Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. Yesterday we added some, I don't even want to say we added some lighting. I basically just showed the rudimentary first step. I did a bunch of stuff on the blackboard so you could understand kind of various lighting principles. And we implemented the very first step in putting some lighting into the engine in just a few minutes. All we did basically was do a radial fall off to show how to light things. And you know, amusingly enough, so today's day 390, so if you're following along at home, use day 389 source code. But amusingly enough, it's surprising, it's always surprising how good fake things look at first, when even if you just get them a little bit correct. It's funny, I think in games, you know, the people who play games are so used to approximations and artistic interpretations of things at this point, that getting things like the lighting equation photorealistic or correct is not even remotely required for people to appreciate the effect. And so here's an example of like the dumbest possible thing. It's literally just a radial fall off. There is no lighting at all in terms of surface calculations or anything. But you can see that even just putting in a radial fall off function already gives a fairly convincing lighting effect. It's like, you know, even just that one little thing, you can already kind of see why it adds something to a game to have some lighting in there. And so that's what we did. Now at the end of the stream, we threw in normals. Normals are the ability in the vertex stream to specify the direction that surfaces are facing. So, you know, a flat surface saying what direction that flat surface is facing, for example, so that it can be used in calculations. And what we're going to do today is just play around with that a little bit to see if we can make this lighting a little bit more accurate by adding the idea that the directionality of the surface off of which the light is bouncing will determine some of the lighting. And we talked about why this was yesterday. Because, of course, lighting is a directional function and has to do with the micro structure of the surface it's bouncing off will determine how the light bounces. So knowing the direction the surface is facing is important, since surfaces bounce light differently in different directions depending on their microfacet geometry. So now that we did that work yesterday, what we would like to do here is have a way of taking into account those normals. And what you can see from what we did on the stream yesterday is in the render group, when we do our push quad function, and again, everything in our game comes through this push quad function at the end, because everything in our game is quads. Our cubes are made up of quads, our sprites are quads that just have an image slapped on them. So everything comes with this function, and all this function really does, right, you can see here, is it just generates 4 pieces of information for the as vertex records, basically, that are streamed out to the graphics card. So this is just writing to memory, and that memory is going to get picked up by the graphics card. That's all we do, right? So if you take a look at what happens in here, you can see that we're now specifying normals, and those normals, we basically generate them by taking a look at the quad and saying whatever the direction the quad is facing, we generate vectors that point in that direction. Now you may ask a very reasonable question, which is, why do we need to specify those at all? Because shouldn't the graphics card just be able to know if we specify a triangle, it knows the triangle is a flat triangle, it knows which direction it's facing? The answer is because most of the time in computer graphics, when we are generating triangles to try to approximate three-dimensional objects that we want to draw, they aren't always supposed to be flat, right? A lot of times you may be generating triangles that are supposed to comprise, say, a person's face or a round ball or, you know, a cylindrical shape, a post, a lamp post, for example. These things are supposed to not be flat. And so what we do there is we say that the normals are specified separately from the triangles. The triangles are used to fill the shape in on the screen, and we try to make the triangles dense enough that you can't really see the hard edges very much. But the lighting would be very obviously faceted if we just drew each triangle as flat, because as it curves around a curved surface, each of those flat triangles is going to reflect the light very obviously differently, and you'd see hard lines. So the reason we always specify normals per vertex, or most of the time specify normals per vertex, is specifically because we often want to specify normals that are smooth across the vertices so that it fakes the lighting to be continuous, right? And it can make things that are comprised out of flat shapes like triangles seem round, because as the interpolation of the normal goes across the surface, you end up with something that approximates a more smooth lighting equation. For us on Handmade Hero, fortunately, we don't actually have that situation at all yet. We don't have to care, so we are actually just specifying the same normal 4 times, and we could be doing something more efficient there if we really cared. On modern hardware, you can do a lot of stuff like specifying the normals in a separate vertex stream that only gets specified once for every n vertices. In this case, it would be 6, 3, 3 for each quad, 3 vertices per triangle. But actually, I guess no. These are indexed, so we would only specify 1 per 4 because these are actually indexed, so never mind. So anyway, that's the idea there, and we are specifying these normals. We're specifying them by taking the cross product of the edges of our quad, and we're pointing all the normals out in that direction to give us flat surfaces, which is what we want. Now, we don't have any way of knowing right now whether those are correct because we're not drawing them. We probably should try to draw them, but we're not going to right now. We're just going to cross our fingers at the moment and see where we get with that. What I'm going to do is I'm going to pop over to the OpenGL code, and I'm going to take a look at the shader that we have here, which is this one. So what you can see here is that we don't even take the normal in yet, even though we're specifying it, and of course we want to. So what I'm going to do is I'm going to start taking in that vertex normal. By specifying here, what it'll do is, remember yesterday at the end of the stream, we specified a vertex n array. Now we're actually going to give that amount point so that when the program code says, hey, is there a vert n array? If so, I'd like to specify it. It will actually find something to specify. We're going to pass that normal through directly because we don't really have anything else we need to do with it. So I'm just going to say we're going to pass a world pose and a world normal. I might change those to world p and world n because I don't really like belaboring the point. So let's just do it this way. There's the world space position and the world space normal. And then when I go through and look at world pose here, we'll just go ahead and make that a little bit more straightforward. In fact, let me just go and replace pose. Oops, replace pose with p. There we go. Okay, so in theory now that should allow us to get normals into our code. Of course, we're not using it yet, so when I run it, we should basically get, if I debug any things we ever under world pose. Oops, forgot to fix that in the vertex shader. Here we go. We should just get the same results we were getting before, so no change here. And the only difference now is that in the fragment shader, we have access to the normal. So we can do something with the normal if we want to do something with the normal. Now, there's another thing that I kind of have to do here that'll temporarily make our graphics be a little bit worse, and that is that the color of our cubes needs to change a little bit. So if you remember correctly, the way that we were doing our cubes in the render group, we actually specified the colors differently per side of the cube. You can actually see in push cube here, we were generating these colors, CT, CB, right? You can see those top color, bot color, CB, CT, all that stuff getting specified here. And that was to give it a little bit of a sort of gradient to make it feel like it was getting lit a little bit in a fake way, right? For the moment, I want to stop doing that. And I want to go back to just sort of overwriting everybody with that same color that's being sent down. And so what's going to happen there, you can see that now we're just getting lighting on the cubes, and there's not any, there's no differentiation between the various surfaces of the cubes, right? They're completely arbitrary. All of them are specified with the exact same color. So all we're getting is those two fixed lights that I'm just playing with right now that are always centered at 0, 0, and you can see that it's lighting everything exactly the same way, right? There's no difference there whatsoever. So that's the thing we got to start with because we don't want that fighting with our lighting yet. That doesn't mean we won't play with that a little bit more in the future potentially, but for right now, we don't want to touch it. So then we go ahead and we say, all right, here's our program, our lighting program. And I'm going to turn off one of the lights for now. I'm just going to use one light. Like so. And this is going to be the light that's in the middle. So there's that light. And I'm just going to now start editing this lighting equation to use those normals that are coming through. Now, one of the things about the normals that come through that's a little confusing, and I want to mention it here because it's going to look like I don't need to do it, but I actually would have in other circumstances, is that this is an actually, I gotta launch Milton. I forgot I rebooted this machine because Windows wasn't finding the network, of course. Where could the network possibly be? So let me go ahead and launch Milton up here and make a little day 390, normal, interpolation. So the normal interpolation here on day 390 that I want to talk about is just, so if I were to take a triangle, right, and I want you to think about the case where, for example, like I talked about before, where there's a cylinder, for example. So here's like my cylinder, and let's say that I was sort of drawing triangles on the surface of this cylinder. So, you know, they look kind of like that. Well, if you take any given part of this here, where two of these triangles sort of meet up, right, like this section here, you've got topology that looks something like this, right? And what we know is this is actually on a curved surface. So the normals for these things are going to bend, right? Each normal is going to be pointing a different direction, such that a given triangle will have normals that are pointing actually in different directions, right? Oops, that one would be the same as this one because it's a cylinder. There you go. Right? What that means is over the surface of a triangle, normals typically will interpolate. And if I took this and laid it on its side, so you could see, here's the triangle laying flat, and I've got one normal pointing this way, and I've got one normal pointing that way, let's say, right, like here and here, mapped to these two. What you would notice is that these two normals, and I'm not drawing these particularly well here, I should probably draw them to scale. We know that they're unit length. So actually, it would be something more like this, right? Now, the way we want to, you know, if each of these is a unit length, the way we want these to work is we want them to work kind of like this, where each time we interpolate the normal, we get a new unit length normal, right? We want the length of our normal to equal 1 at all times. The reason we want to do that is because we're going to be taking dot products with it and doing other things where we don't want its length to affect our computation. So we want it to be length 1. Unfortunately, what's going to happen, remember, is when we pass these down, it's just like everything else, like fragment color and that sort of stuff. Whenever we have a vertex shader that outputs something to the fragment shader, that something is linearly interpolated across the surface. Now, it's not strictly linear interpolation because remember, we get perspective correction in there. So it's actually not really linear interpolated, but it's linearly interpolated in world space, right? It's just not linearly interpolated in screen space because of perspective correction. But you put that out to the side right now because all we're talking about at the moment is interpolation in world space that we actually care about. And so that will be happening linearly, just like the stepping along the triangle happens linearly. For all intents and purposes, you're never going to get something that lies off of the line, off of the triangle, right? Everything's going to be on that triangle. The same ends up being true for normals. So the normals will also be interpolated in a line. And what that means is, let's take a very exaggerated case. Here's one edge of the triangle. Let's say we had a normal pointing that way and a normal pointing that way. If you look at what's happening here, in between those two, we should get a normal that looks like that. What we're actually going to get is a normal that points, yes, in that direction, but that's much shorter, right? It could be, half the length that it should be. So instead of a length of 1, instead of the length of the normal equaling 1, the length of this normal is going to equal like 0.5 or something, right? So not only that, but we're not getting spherical interpolation here, so we're not getting, that. So as a result, when you interpolate linearly across this, you're also going to get a difference in acceleration of the normal. So instead of a smooth rotation through here, it's actually going to have more at the points than it does in the middle. It's going to get faster in the middle, meaning the interpolation of the normals is going to change more dramatically than at the end, simply because a line is getting projected out to an arc, and that's what happens when a line gets projected out to an arc, right? You can see this yourself just by drawing it, if you draw it like this. So let's say I have this, and I take an even number of steps along it, like so. Right? So here these are roughly equivalent steps. If I then look at what happens if I were to actually take the real arc here, right? If I extend those outward, look at what happens. Well, you know, this is a really bad diagram. I'm gonna have to do this a little bit better than that. Okay, I'm gonna try really hard to draw a really good diagram here. Heaven help me. This is the worst circle ever. Okay, so this part looks sort of circular, let's say. There we go. So let's say we were going to take and use this as our interpolation, right? So here's the halfway mark. Here's the halfway mark there. Let me see if I can do this. All right, so I'll try my best to make this work here. I need like a ruler tool or something. Oops. So I didn't do as good as I would have hoped, but it's still good enough, right? So hopefully you can see the difference in speed that's happening there, right? The distance between these two, for example, is much less than the distance between these two. And so that's what's going to happen when you linearly interpolate what is meant to be a spherical quantity. You're going to get the angular interpolation is going to get much more quick in the middle of your things and much slower towards the end, right? And so normally what you have to do with normals, is you have to renormalize them in the fragment shader or come up with some other encoding scheme that's going to interpolate properly, right? You have a lot of different ways you could approach it, but you know, the simplest one would just be let's renormalize in the middle of the shader. When you do that, what you're effectively doing is doing this projection outward, so the speed is wrong, but everything else is fine. So all the rest of the calculation is right. It's just the interpolation is a little bit more wonky than it should be, right? But for our cases, we have a much better situation. We only have cubes, right, and sprites. They are both flat, which means that for each primitive, we never round anything. We're always drawing a flat face on something. So our normals are always pointing the same direction, which means not only do we not have to worry about that speed problem because we're not interpolating between anything, they're just constant, right? But we also don't have to renormalize because the length will stay 1 because they're not actually bending at all. And technically, if we wanted to, instead of this being smooth out, we could probably actually have this just be flat out. But I don't want to push my luck and start using lots of different qualifiers because who knows. Anyway, so I'm not going to have to do any of those things that I just said, but I want you to be aware of them because if you're doing your own stuff here and you want to make a curved primitive, or if we ever have to make a curved primitive on Handmade Hero, we'll have to be aware of it. All right, so here's our light distance fall off. Here's the amount of light that we have here. Now what I want to do is I want to break up this equation a little bit. So the distance equation, right, we all know what the distance equation is. In this case, it's the p minus, I guess we should say the p of the surface minus the p of the light, right? We're taking the length of that. That's the distance. But the problem with this equation, right, is this produces a scalar that just tells us how far away from the light we are, but we need more information for that now. We also need to know what direction the light is shining on us, because we want to start to talk about these surfaces, and now we have the surface normal, because we specified that, and we know what point on the surface we're talking about, but now we need to know some things, right? We need to know where the viewer is, right? We need to know where the viewer is, and we need to know where the light is. because we want to start constructing a reflection equation here that'll tell us how light is supposed to bounce off this surface. So we've got this, we don't have this, we don't have this, and we need to start getting them. Now, we did produce essentially this, because this equation right here, taking the length of PS minus PL, well, what's PS minus PL? Well, this is PS, and this is PL, right? So if we did PS minus PL, we would get this vector, which is the inbound lighting vector, which is exactly what we want. If we want an outbound lighting vector, we could just switch these two terms and do PL minus PS, and we get that vector. So whichever vector we want, we can get it pretty easily, and that's great, right? So without doing any more work, if I literally just pull out this equation into two steps, excuse me. So here's my vector that goes to the light. I can just say light P minus world P, right? And now I can normalize this essentially for free because I know I have to take the light distance. So I can say, you know, length, and you'll forgive me for never remembering what the GLSL intrinsics are. GLSL reference card. Here you go, just length. So if we take the length of that to produce our light distance, we then know that we can normalize the vector to the light by just saying I want to take 2 light and I want to divide it equals it by whatever that light distance is, right? So this produces a normalized 2 light vector. We know we have a world n vector. So now we at least know this and this, right? So even with just that, if we assume a perfectly diffuse surface, we could go ahead and dot product these two together to emulate a fall off of the light as it approaches a steeper angle to the surface, right? All right, so let's take a look at that. So right now we're doing this. Let's just rerun this here to make sure that we're still computing the fall off properly, right? Because we haven't changed anything. The fall off should still be right, and it does look right, so that's good. But now what we want to do is take that 2 light vector, and I want to do the dot product of the 2 light vector with that surface normal, right? So now we're going to be producing basically, remember how many times we talked about the dot product in the past? Well, it's coming back. It always comes back, right? So now we've got essentially this 2 light vector. We'll call that L. We've got N with dot producted with L, right? That's what we're producing here. Now, what does that give us, right? Well, we've got N and we've got L. What does that give us? Well, everyone who has watched Handmade Hero had better be saying it out loud right now. It is the length of N, the length of L times the cosine of the angle between them. The angle between them is right here, right? And anyone who didn't just say that, who has been watching the series, I'm going to personally come over there and slap you about the face a little bit. Just a little bit. Not enough to leave any kind of bruises. Okay, so the length of N, length of L, cosine theta is what we're going to get out of that. Now, what did we already say? Well, this and this have already been normalized, right? Length of N is 1, length of L is 1. So neither of these two things is going to contribute to this equation at all. So all this will compute is the cosine of the angle between them, right? So this is the cosine of the angle to our light source right here. And that is exactly what we would need to simulate the inbound lighting equation, right? Meaning, if all we wanted to do was pretend that all this surface did was radiate light in every direction whenever light hits it from any angle, so a completely diffused, perfect chalk surface. Well, remember what happens is that when light comes in, it comes in, you know, as light hitting the surface. When light hits the surface, the angle to the light at which it hits the surface, right? Here is the angle at which it hits the surface. The cosine of that is going to be, oops, I wrote that in the wrong way. There we go. Here is the, I gotta draw this better. And in fact, you know what? This has always been confusing to me for lighting equations. So I might work this out right now just to satisfy my own self. Let's just do this out the whole way because I'm interested to do it. So first of all, we have an inbound light, right? And the inbound light is coming in at the surface, and we can assume that when it strikes the surface, if it's striking it from a particular direction, the cosine rule should still apply, right? So here is the inbound light, and this triangle here, right, this is the lighting direction. There's theta, right? And the right angle of the triangle is right there, yeah? So here's the hypotenuse, right there. And this right here is the amount of light that's striking the surface in that sense. So it's spreading the light out on the surface proportional to basically the inverse of that cosine, right? So this right here is the cosine of theta, or I should say h cosine theta. So if we assume that this was just a unit size, right, we would just have cosine theta is the spreading function of this light. So all of the light that comes in falls on cosine theta's worth of surface. Right, or sorry, I should say, cosine theta worth of light falls on a unit length surface, right? So 1 to the cosine of theta, if you will, right, equals, you know, surface light over incident light, if that makes sense. This is the part that I've never really quite understood about lighting equations. I don't do a lot of work with them, so I just wanted to sort of write out the equations for my own amusement to see if they line up intuitively or if you have to go make a special leap, right? Now, for the viewing direction, you also get another situation, right, where this exact same thing happens. So whatever angle I'm viewing at, and this is cosine phi, this is like a different, this is going to be a different angle, right? It's the viewing direction. So this is the light up here, this is the viewer coming in here, right? So the viewer, on the other hand, is viewing 1 unit's worth, right, how to put this, 1 unit's worth of the surface is going to go out on cosine theta's worth of space, right? So if you think about how much light you're actually getting out on this shaft, you should be getting more of the light, if that makes sense. I don't know if this makes any sense. Right? So really this, and I shouldn't say theta, I should say cosine phi. Right? So there's another angle that's the viewing angle there, right? So the amount of light that comes out that you're seeing that coming off of the surface, in this case, I feel like the amount of light coming off of the surface should be proportional to the inverse of that, because again, you're going to end up with a situation of 1 over cosine phi, right? This is the surface, again, and this is the width of the band, right? This is the view, if that makes sense. So if I had to do something completely ridiculous here and just say, I want to take, you know, the incident light that comes in, right? I want to multiply that by the ratio of incident light to surface light, right? I want to multiply that by the ratio of of view light to surface light, and in so doing, transform incident light into outbound light, right? What would that equation look like? It would be like incident times, right, surface over incident, which is 1 over cosine theta, times view over surface, which is cosine phi, cosine phi over 1, equals my viewing amount, right? Equals the view light transmission. And so looking at this, I would say naively, not looking at any graphics textbooks and having no idea what I'm talking about, right? I'm literally just pretending I have 2 surfaces, and I'm just seeing what would happen if I just write the math out. No preconceived notion here whatsoever. Then I would get incident light times cosine phi over cosine theta equals the viewing amount. Right? That's what I would naively expect to see in my lighting equation. And what are these 2 things? Well, that's basically saying that I have whatever my light strength is, right? This is my light strength, you know? So my light strength times the cosine of the view angle over the cosine of the light angle equals the viewed light strength. So yeah, there you go. That is the naive person's wrote out the what should happen to the amount of light that gets like bounced off a surface if you just tried to write it out as if you literally had like bags of photons coming down a beam and you wanted to know what the proportional transfer to that thing was, right? And so I don't know if that holds a lot of water. I don't know if that's at all correct physics-wise, but that's just what I would assume. And looking at that, you know, let's see what that actually does. So if we assumed, for example, that the light comes down at this cosine theta, right? As that same light band got, you know, steeper, if that makes sense, you're shining quite a bit less light on it. So as this goes down, you get less light. And the same would be true of the other way around, well, no. So as the viewer gets steeper down, you're seeing more of the surface as a result. So the opposite's true of the viewer, meaning as the viewer gets higher up, you're seeing more of the unit area of the thing, right? So I don't know that that squares with what I expect from the standard textbook lighting equations, but it seems like an interesting, like, I'm not sure where the logic is flawed there, so it seems like that's roughly what I would expect to have happen now that I think about it, right? I mean, I can't say I know why that's wrong. Yeah, I would be interested to check. I would be interested to check this against the physical lighting transfer equations. I don't know that we have those in a particularly convenient form that we can go look at, because I would like to see a real explanation of this. Like, I'd like to see what the actual physical behavior is there worked out, because I feel like this seems reasonable, but I don't think I've ever seen it written that way before, so I'm assuming it must not really be how it works. But that seems relatively sane to me. I don't know. Anyway, so we'll leave that as an exercise for a little bit later, because we'll have to check some reference material when we get into maybe some other lighting stuff. But for now, I'm fine with it. We can go ahead and implement this, and it'll just be interesting at least to see what the deal is. So cosine phi, cosine theta on the difference between those two. And so we already know how to implement one of those, which is the cosine theta portion of that. And so that would be 1 over cosine theta would be the incident light, right? Which is to say that if the light is directly down, so if that angle, and I guess to be clear here, we need to talk about how we're measuring these angles exactly, but I'm measuring the angle on the inside right now. So the 90 degrees, right, and this is a little bit confusing. So yeah, how does this work when cosine goes to 0? We want cosine to go to 0 at this here. So we want this to be cosine of 0. We want this to be cosine of 1, right? Which is exactly what I guess we would get in this case, because cosine, if you think about it, right, it starts at 1 if it's pointing in this direction and goes to 0 when you get here. So what we kind of need to do is measure the other way around, but that's exactly what our dot product will actually do, right? Dot producting with the normal of the surface is actually going to measure it in this direction, right? So I think that's exactly what we want to do anyway. As far as I can tell, yeah. So basically, as this angle goes down to 0, this will clamp to 0 as well, and it would be increasing as this kind of comes up to 1. This would be 1 over 1, right? I would think, and then as it goes to 0, it gets much higher. What's weird about that, and which doesn't seem to make much sense, and maybe this is why I've messed the math up here a little bit, is we can't, if we have a divisor there, but it feels like we should have to have a divisor there, because again, one of these two things has to be a divisor, I would think, since I don't see how they could both be on the same side of it, is that makes it so that these values get very high eventually, right? Which doesn't make much sense. Like, we want these to be on top, they make a lot more sense, right? Because if this is on top, then we have a very well-behaved equation. When this is on bottom, we don't. But I don't see a lot of ways, like, I'm trying to think of exactly how we get around that. Maybe I need to link these up in a slightly different way, right? Maybe I can't string them in this particular fashion. Like, for example, if this was cosine theta cosine phi, that is always well behaved. And it doesn't have weird behavior like making this term get very large as the view angle decreases, which is what would happen here, which doesn't really make any sense, right? So just thinking about it, I must be thinking about that wrong in the way that these things get related, meaning there must be some way to relate these in a way that isn't talking about the ratio of incoming versus outgoing in that sense. But I'm not sure exactly, again, what it would be. Because it does seem like that's still how you would think of it, right? Let me just do this one more time and see if I can make a little bit better sense of it. Again, I always wanted to understand this, and I've never really spent any time looking at it. Rendering people have to do this all the time. So, you know, presumably they would know how to do the right diagram here for thinking about like micro shaft of light. But let's measure this, and let's measure it correctly the way that we're going to measure it, which is like this. So there's theta there, right? Because we're going to be doing that as the way to get our cosine. So we kind of want to measure it from the top down, if that makes sense. Okay. So if we were to assume something like this, where we are pointing directly at the normal, right? Then a unit amount of our light falls on a unit area, and that makes sense because the cosine of theta in that case is the cosine of 0, which equals 1, right? And that means that 100% of the light that hits the surface is eligible for use, right? Rather, you know, a single amount of area is going to reflect the complete amount of light, right? That those photons all in a whatever unit width of light is are going to hit the surface, right? Now, as we move over here, we're going to end up looking more like this, right? And now, for the same amount of incident light there, it's going to fall on, I guess I kind of see how this is more logical. So if this remained the same and this got bigger, right? Meaning as that rotation goes down, if we kept the same size here, right? So that's probably where I messed up in my thinking. So let's say we're talking about the same unit area, always here, right? Like so. Now, if I slant this over to the side, like this, right? As I go further to the side, the size of that light gets smaller and smaller, right? The sort of that gets smaller and smaller. Because before, it was equal to the whole size here, same size as the surface. But as it gets more and more incident, it gets equal to a much lower amount, right? It gets equal to a triangle that looks more like that, right? Where this is theta out here, right? And if that's theta out here, there we go. If this is theta out here, then I assume I can do, what I need to know is what's this in here. So that's actually, this right here, this angle, is going to be 90 minus theta, right? And we would want the cosine of 90 minus theta there, I assume, right? Because this value is not really super relevant to us, is it? I mean, I can't see why it would be, because it doesn't really have anything to do with the shape of the light. It's this one over here. So it's the cosine of the theta on the inside there. And that, yeah, that really does seem to be like it would be the wrong way around. What's interesting about that is that's a sine, isn't it? Which, again, doesn't comport with what I would assume to have happened with the lighting here, right? So that's a little bit weird to me. If I wanted to know how much light source was seen by this unit area, the amount of light source I'd see is going to be the sine of theta, I would think, not the cosine. And furthermore, it's actually the negative sign, right? So that's peculiar. So that's a little bit closer to what I would have expected, but again, it's a little bit weird. So I don't understand quite yet, again, how to draw that diagram in a way that makes good sense to me. I do see that my mistake before was not, I need to think about a unit area on the surface, like a fixed area on the surface, and thinking about, right, the difference between that and that. And you can see that that same size of the surface, in terms of how much of the light area it can see much less. Because here is the window of the view that this unit area gets on the light source, right? It's the same size as the surface area. So that's the 100% case. 100% transmission, or 100% reception of the light from that surface. But at the angle, right, we're only going to see that much. And that makes really good sense to me. And if this were the angle we were measuring, which is the angle from the surface out to the light source, right, then it would make reasonable sense. Because that is the value we're trying to measure, right? And isn't that how we would have to have measured it, right? Because, but then again, thinking about it, it actually works properly if it's cosine theta, because if this angle here is 0, cosine will be 1. If this angle is 90, it will be so am I misthinking that? Here's the right triangle that we're trying to make. And that's usually, right? Oh, no. No. I've just got it turned around. So, okay, we're all good. No need for panic. If I actually turn this around, right, this is cosine theta, and that's sine theta, right? So we're okay. It was just the fact that the diagram was upside down and me being a little bit slow today that was the problem. So that does make good sense then, because cosine of this angle would give us this, and we don't want that, right? We actually want the sine of that angle. But hey, it turns out we're measuring this angle, so that's absolutely perfect, because since we're measuring this angle, this would be that triangle, right? It's that triangle right there. And that is the cosine of that angle, right? So that's pretty nice, actually. Okay, so that to me seems right. So I would say that the amount of light So the amount of incident light is going to be proportional to the cosine of the angle, right? And I'm happy with that. But now let's ask the question, what happens on transmission, right? So now I want to know, okay, now I've got a viewer, and a viewer is going to look at this thing, and it seems to me that the same thing should happen, right? So if I'm talking about this much area that I'm viewing, well, if I'm viewing it straight on, then I should be collecting all of that, I should be seeing all of that light that's getting, well, I guess, So this depends on how we look at it. So the light that comes in, how much you can see of the light source, how much you can see of the eye point is a tougher question, right? Because this stuff is getting evenly... Now, but I think that's probably true, right? If you assume that every point on this surface, right, is radiating equally in all directions, then in theory, as long as you have all of the light points in there, it shouldn't really matter what the width is that you're viewing. I don't think. So it doesn't seem like the viewing angle would change it at all. Meaning the angle of the view, in this case, doesn't seem like it would apply. So it seems like you only have the cosine theta term on the incident light, because the incident light is how much of the light source you can actually see. When you're talking about the viewer, well, the viewer, I don't know that it would necessarily have that same effect, because the viewer is collecting whatever gets thrown at them. And I guess the collector size is changing in some sense there. That's a really hard one to think through. I'm not really sure how to think about that one from first principles very well. But yeah, so I don't really know. So in some sense, I could see you multiplying by cosine phi, because the same thing is true here. The size, the area on which you're sending that out to the viewer is going to be smaller. But at the same time, I think maybe there's an argument that you wouldn't do that, because if this is actually a uniform distribution function, which is what we're starting with here, because we're not yet talking about the surfaces, the surface properties. We're assuming that the surface radiates light in all directions uniformly. It's perfectly diffuse, because we can talk about later making it not diffuse, right? So if we think about that, I'm just trying to gauge, at that point, if it's radiating equally in all directions, as long as you're collecting everything from there, from the same size, it doesn't seem to matter that it's coming back in a smaller area. No matter what the area is, the total brightness is still the same coming back. Now, I could see an argument being made that you would collect more, because the same area on the collector is collecting more here than here, right? Because let's say you took the same size area that much. Well, when it's looking straight down, the same size area back is looking at a lot less light than from the side, which is collecting more light. So it almost feels like it's an inverted scenario. Like the smaller it gets, the brighter it should get, because a smaller amount of looking at it is going to collect more light, right? So this is a bit of a puzzler. I feel like this one really wants to be researched. I feel like we should go read a physical rendering explanation of the reflection, the differential reflections calculations here, to get this right, because I'm not sure I could really say. I feel like that's a little bit above my pay grade in terms of rendering tech to say what should happen there. But it feels like there is sort of a need to compensate for that. And I feel like going back to thinking about photons bouncing around, you know, when we talk about the surface area, a differential surface area, you know, photons coming out of the light source, well, this band is going to collect a lot more photons than that band is. So it makes a lot of sense to say that the amount of light incident on the same amount of area on a surface is going to be proportional with the cosine theta to the light source. And the reason for that is just going to be that the cosine theta to the light source tells you how wide the photon collecting band was for the same surface element, right? But for viewing, we're talking about the fact that we're sort of viewing this whole surface, right? So we're talking about pixels that are collecting the light that's bouncing back at us here, right? And so when we talk about collecting from the surface, it seems like what should be happening is that as you get more oblique to the surface, it should be looking brighter to you, right? I mean, I guess what I would say about that is I mean, I'll be honest with you. Just for, again, I wanted to work this out from first principles rather than looking at somebody's explanation of it because I just wanted to like have that experience. I've never done it, right? And I'll be honest with you, just looking at it from first principles, it just really feels like there's going to have to be an inverse relationship there. And again, I'm probably just wrong about that because my intuition is probably missing something. But here's my explanation for why I would think that's the case. Let's take a weird scenario where we're just saying, here's some surface, right? And we've preset how much light is emanating from this surface, right? And we're saying it's uniformly scattering in all directions. So the same amount of light is getting scattered in any direction you happen to choose to look at this thing, right? Well, if I was to put my collector directly above it and the collector is this size, then I am going to get all of this surface's light that it has to contribute in that direction, right? I'm missing all the light that's going in the other directions. I'm going to have this much, that big of a band worth, the whole surface's worth, is going to fall on my entire collector, right? So however much is falling on a particular part of this collector, let's say however much this light is that it shines off in one direction, if that's L, then I'm going to get whatever the width of this thing is, I'm going to get L over W, right, as the amount of light per unit area on my collector, right? Again, really just being dumb, being a dumb non-graphics programmer, that's just what I would think, right? And then if I take the same collector and I move it over here, right? So now, the collector looks like this, right? Well, if I take a look at what part of this I could see, it's actually the same amount of light, right, is falling on a much smaller part. Now remember, this is supposed to reflect evenly in all directions. So I'm seeing the same amount of surface, and it should be reflecting the same amount of light out in all directions. So in theory, right, shouldn't this now be, maybe that's half the width or something? Shouldn't this be L over width over 2 or 2L over width? So shouldn't this thing now appear to be brighter than it appeared before? It seems like a dumb result, so I'm guessing the answer must be no, that's stupid, and here's why. But the here's why part, I don't know what that here's why part is. And I guess one way to think about it is it's not collimated light. So really, you're getting a cone of light and it's going to fall on the whole thing, right? And in both circumstances, it's going to fall on the whole thing. And maybe that's the answer, is that since it's uniformly radiating out and not collimated like that, that you always will pick up, from any point on here, you're always going to pick up that much of the light that's coming out, right? From any point on here. So it's always uniform, because no matter how big of the light source you are, each infinitesimal point on there is always projecting out towards someplace on here. And you're always gonna, that integral will always work out to be the same. That's the best I can do to convince myself that there wouldn't be a term in there. So I'm going to stick with just the cosine for now. Since I'm relatively convinced that that's the correct term for the incident light, I would like to look at the viewer equations. I might take a gander this week in between episodes to take a look at a physics rendering text to see what their explanation is, because I'm assuming that they have a good way of explaining why there presumably isn't a angular term to the reflection, again, prior to calculating any kind of surface property, right? Obviously, surface properties introduce angular coefficients, but we're not talking about surface properties yet. We're talking about if you factor the surface out, and you're only talking about the angle, the direction of the light and the viewer, right? So anyway, once we have this dot product of the light to the world, like that, at that point, we know, since we're going to the light and we have the world number, those pointing directions, one of the things that we're going to have here is this can be negative, right? So if this is my surface and the light is over here, right? It's coming from behind. Then when we compute the angle to the light and we dot product these together, we're going to get a negative value, right? This is going to be negative something, you know, like negative 0.6 or something, right? So what we need to do here is after we take that cosine, we need to clamp it, because once the light gets behind the surface, it can't shine on the surface anymore. Unless this surface was transmittive, so light coming from behind it passes through, so it got translucence, we shouldn't see it, right? So what we want to do here is we want to use a clamp, and there is a good clamp in here. OpenGL provides that by default. So here's our clamp, right? We can say clamp this value to a min and a max, and that's all we need to do. So we can say cosine angle equals clamp of the cosine angle between 0 and 1. And so if we clamp it between 0 and 1, now we know that if we get behind the light source, it won't contribute. So now all we need to do is take what we were previously computing to be the light strength based on fall off, and now we just use the cosine of the angle to determine what the angular reflection should be of that light. Now, if we've actually specified our normals correctly, oh man, that doesn't look like we've specified our normals correctly. It looks like our normals are coming through as 0. If we actually specify our normals correctly, we would have gotten a good result there, I suspect. But at the moment, it looks like our normals aren't. And so what you can see here is we did do 2 light, so this is the direction from the world to the light, right? And here's the distance. We normalize based on that distance, so that should produce a unit length light vector there. We can also phrase this way, which is a little bit better. It shouldn't change result at all, but it's just a little bit better way of saying it in terms of normalization there. So basically what happens is we multiply the vector by 1 over the light distance, so we don't divide each component, we multiply each one in case multiply is faster. We then take the cosine of the angle between them by dot producting the thing to the 2 light and the world. Oh, you know what though? No, actually that's fine. And then we take the cosine of the angle and we clamp that between 0 and 1, right? And I believe I put those parameters in the correct order, right? It's x min max, right? Yeah, so x min max. And so after that, we should end up with the correct value for cosine angle, but we're obviously not getting a good result from it. Excuse me. And so the question is, why not? My first suspicion is that our normals are not coming in as correct values, right? So what I'm interested to see here is if I was to go ahead and say that everything points up, directly up, so world n is 0, 0, 1, I just want to see what happens there. Okay, so it's the rest of our equation that's busted, it looks like. So let me go ahead and debug why that is. So let's say I set cosine angle here. If cosine angle, if I overwrite it with 1, we should be in a situation where we get our lighting back, right? Yeah, so that's what we would expect, and that is what we got. So now let's say, well, if we take our cosine angle prior to clamping, just to make sure that the clamp isn't the problem, If we take our cosine angle probability to clamping and set it to be 0.5, or rather even if I just set it to 1, I should get full lighting again, because it should just pass through as 1. It does, so that's good. So then I've got our dot product of the 2 light with the world end. So let me set both the world end So now we're assuming that the light, oops, I wanted to actually make these both be z. So now we're assuming that the light and the world normal are both pointing straight up. So we should get one here as well, and we should have the same lighting. And so now what I'm going to do is I'm going to knock out the normal part of that to see what happens if we just set the 2 light. And so if I knock out the world end part, I get 0. If I knock out the 2 light part, I get, oh, not quite 0, but a very odd sort of behavior there. One thing that's true is our light probably needs to be up above us a little bit more. So let me go ahead and make the light be a little bit higher up, because it might just be in geometry at the moment. There we go. Okay. Oh, wait. Okay. So now if I go ahead and see what happens, let me restore world normals to be pointing directly upward. So if I make world normals point directly upward, we do collect light, right? And we get some fall off of the light distance, so we may have to up the light strength a little bit here, just to still, because I put the light up a bit higher, so I'm just going to make the light a bit stronger. So there you can kind of see us lighting. One thing that's a little weird about that is I'm not really sure why the light amount changes so much based on the height, because the height difference shouldn't have been that great for these things. I wouldn't have expected it to quite be so dramatic in terms of the distance should have been smoother there, I would have thought. It doesn't make a lot of sense to me, to be completely honest. I think we've got other problems, to say the least. So a couple things here. First of all, yeah, I was seeing in this situation a lot of color changes based on the distance to the, based on the viewing angle, which I don't know. I mean, there could be fog effects involved there, but I wasn't expecting to see that. I guess that might be fog. I don't know, but like, see how these are getting darker as I get oblique to them, and I don't really feel like that should be happening, right? That should not be occurring, I don't think. With the radial fall off, you wouldn't expect the small height difference to make such a pronounced difference, but it's not out of the question, I suppose. That it would, but anyway, let's take a look at what happens if I nuke both of these. So the 2 light and the other one are both the same. Do I still get that? You can still see that even if those are, even if we're just using the distance fall off. So let's see here. If all we're doing is distance fall off, so cosine angle is always going to be 1 in this case, in theory. Even in that case, we get some interesting effects there. So let's say, let's just clamp total light to 1. So now there's no lighting at all, right? It's just flat. What happens if I do that same behavior that I was doing? Do I get darker here? So you can see I don't get darker. So something weird is happening, because if I'm setting the cosine, this light distance itself appears to be changing based on something that it shouldn't be changing based on, right? Because this light P, world P is supposed to be just pass straight through. It's not supposed to have any relationship to the transform of the camera at all, right? It should not be it should not be related in any way to the transform. So let's take a look at this shader one more time. So here we go. We take our vertex, right? And we produce the proper homogeneous coordinate version of the vertex, because remember, we store the z bias in the w coordinate. We pull the z bias out, and we set it to 1 in the w coordinate. We then create a z vertex, which is our vertex. That's just our vertex biased up by the z amount that we want to bias. So we're pretending it's in a higher place than it is, right? We then transform both the vertex that we started with and this vertex that we've artificially bumped up with the bias. We transform both of those. And that will transform them by the camera transform to view them wherever we're going to view them by. We then go ahead and take the modified z as being our, we do basically the transform that we would have done to produce a correct z value for our result, right? For our synthetic result we're going to pass through. But then we take just whatever the z vertex was that we initially fashioned with its artificial z value there, right? We take that and we pass that directly to the shader. So that should not, none of this work should affect that. It's just got a z bias added to it, and that's it. And by the way, the cubes which we were seeing the weird sort of artifacts on, those are not even, don't even have a z bias. So those are just 0, right? We then pass that through to world P, which is supposed to be interpolated, and presumably is being interpolated properly. We set a fixed location in world space for the light, which is just the center of world space, 004, right? And then we take our light and we just look at what the distance was from where we are in the world, that sort of what should be a normally interpolating value in world space, linearly interpolated value in world space, and we take whatever the light location was and we subtract them. So yeah, I don't know if there's anything particularly strange with doing it that way. I mean, I can't think of anything strange that would be going on there. Why the distance to the light source would be changing based on the view angle there. I really can't. So let's go back and just verify that that really is happening though. So if cosine angle equals 1, so basically we're just using light strength over light distance times light distance, so the squared light distance. If that's all we're doing, then what I was observing before it just seems like it's getting darker as I rotate upwards. Is it possible that that's just an optical illusion, I guess? That that's just because they're getting closer to other parts of the... I guess that could just be an optical illusion. Let's see if it is. That could be one of those optical illusions. So here I'm going to do shift print screen. And I'm going to open up GIMP. There's GIMP. And then I'm going to go ahead and do that rotation downwards. And I'm going to do another shift print screen. And then I'm going to paste that as a new layer. Then I'm going to crop it. And I'm going to put these next to each other. And I'm going to look at the values of them. All right. So here's like the edge of this cube, the corner of this cube here. And it's 38, 60, 39, right? All right, it's just an optical illusion, I guess. Wow, that's crazy, right? Oh, eyes and color. They don't really work. All right, so maybe that's correct. I'm willing to give it the benefit of the doubt for now, so that's fine. But man, that's weird. All right, so let's get back to debugging. Now I can not freak out that there's something wrong there. So really, we just have to figure out what's wrong with our cosine computation here, because it's obviously not working quite correctly. So the world normals, it would be nice to verify what direction those were pointing in as well. But for now, let's just get back to the start. So if I'm going to fix both of those normals to be pointing upwards, I get the same result. If I switch the world normal, but not the one that goes to the light source, right? What does that give me? So that appears to give me some actual lighting correctly. The calculation of making the light go to the light source seems to, I'm sorry, the calculation of fixing the normal seems to be good. If I, oops, I don't need to do that. If I instead fix neither of them, so if I don't fix the world normal, then I get black. So it suggests to me that my world normals are just not coming through correctly, right? So I'm wondering if invert, I never passed it through. So of course there's 0. So now I'm actually passing it to the fragment shader rather than leaving it set to 0. Okay, so there we go. So now our light source is reflecting more correctly, right? And hopefully you can see from that now we get a lot more of a sense of lighting too as well. And correctly is the wrong word here. I don't actually mean to say it's correct. We're just probably more correct. We haven't done any testing, so who knows. But here you can kind of see if I look at it, right, the light source is directly above. I get almost no lighting on those surfaces because they're totally oblique to the light, but I get plenty of lighting on these other surfaces over here, right? So that's a more reasonable direct lighting calculation. It's not the lighting calculation we're going to actually want to use, and the reason for that is because of ambient light, and we'll talk about that a little bit. But we're starting to get more of a definition here to the surface, right? Now let's talk a little bit just for a second here. I want to sort of add the ability to test this out more. This is not what we're going to want to do at the end of the day. So I don't want to make it sound like this is actually something that's going to stay in here. But temporarily speaking, I would like the ability to move the light around as well, right? And we're going to want to do something a little bit more fancy for moving the light around in the future. So this is not a good example of how we would be doing that going forwards. But if I come in here and where's my render group? Where's my settings here? So here's my render setup. If temporarily speaking, I just did like a v3 debug light p, where you could set the location that the light was coming from, for example. If I wanted to add something like that, I certainly could, right? And what I would need to do there is go into the OpenGL stuff and take a look at where we set, say, for example, fog color. And so something in here, we would just add another one at the end that we're just going to use just very temporarily. debug light p. And that is something that, again, is just now where we had this light p here. I'm gonna pull that out and say that's a uniform. Okay. And so I'm just going to say that we've got a debug light p in there, and that's for our z-bias program. That's something that's going to show up here. And then whenever we use that uniform, whenever we use that program, we can just set it. Like so. What is the problem? Can I convert const GL float star? I don't know why this isn't wrapping anymore. Oh, it's wrapping at the wrong size, I guess. Cannot convert argument 3 from v3. Okay. Bet you can now. So now what we have to do is actually set that in the render group. So in the render group, when we pass this down, we set camera transform. We're going to need a way to control these things better, but debug light p. Let's do this. And so now when we run the game, we should get the same results with the light is kind of in the center of the world now. What we want to do is just put that somewhere reasonable. So if we pop over to world mode, where it sets like the near clip plane and stuff like that, we can also set the debug light p. And so in here where we set that, and hey, guess what? If you want to set that, you've got to actually set it to something, as it turns out. Where should that get set? Probably just right here. So yeah, if you take a look at what's happening now, we're back to the original, and now we can move the light around anywhere that we want. To move the light around, I'm going to probably just attach it to the hero for now, I guess. And so we know where the hero is standing in a sense, I think. Probably, maybe, do I? I don't really remember to what extent we actually know that. Once we do the simulation we do, so here's the camera entity here. So if there's a camera entity, I guess we can just say like, hey, whatever the camera entity whatever the camera entity's position is, that's all we really wanted to know, right? So we want to set the light position to that. So I'll just go ahead and put one in here. And we'll just specify it that way. And we're probably going to want to bias it up a little bit from that, because that'll be just where the person's standing, I assume. Why am I not seeing that move? Oh, camera entity is not what I guess I mean. No, that is what I mean. So camera entity should be correct there. I'm gonna have to see, oh, right, world mode. That's the problem. There we go. And so what we probably want to do here is just also bias this up so that it's kind of hovering above Maybe that's a little bit too much. That's probably not where the hero's head would be. That's probably more where the hero's head would be. All right, so there we go. So now it's basically like the light is just on the hero's head as the hero moves around. And you can kind of see that light falling on the surfaces more correctly now than it was before. And you can actually see a lot of definition in those surfaces too, right? Like I said before, even just basic lighting that's not very good yet, if it obeys some of the basic criteria for lighting, produces relatively nice results, right? So that seems pretty good so far. Now, there is some weirdness there that doesn't make a lot of sense to me. I'm gonna have to think about that. So that is wrong. We're gonna have to think about why that's happening. Like, those trees should be basically black, I think, because they should be pointing more away from the light than they are. And I guess maybe the thing is the light's kind of now up high enough over them that it's not. So I could maybe convince myself that that was correct. And I guess when you look at it like that, you can see why. And I don't know if that means we want to bias the lighting calculation using the z-bias in a different way as well to maybe make that a little bit different. But you can kind of see that that's, you know, giving us some of that first step to reasonable lighting that we would want, right? Now, one of the things that you'll note here is that this is giving us lighting from only one light source, and we want to get lighting from more light sources than one, and we also need some other, in order for our lighting to be reasonable, we're going to need a little bit more sort of, I don't want to say realism, but softness to the lighting. And so I want to talk a little bit about that in a second here, now that we've sort of established basic lighting. And I've gotten that to the point where I'm relatively happy with it, right? Like this is all you can really expect from trivial, trivial lighting that doesn't do anything beyond the standard diffuse lighting equation, right? So let's talk a little bit about just what we need out of our lighting going forwards, because this is probably the two things that we'll try to get over the next week or two. So better lighting. So the two things that we really want out of here is one, and you know what? I guess I'll say that we could get three things even. One of them I don't know if we actually want / care about, but we'll talk about them anyway. So one is we want more lights. So the way that we've done the lighting right now, our equations are good. So, you know, we can throw more lights at it, but we're going to have to loop over all the lights that there are. So we probably could get away with, you know, doing 8 lights this way or something like that, and it wouldn't be a problem. But if we wanted to scale up to like, you know, 100 lights or 200 lights, it wouldn't work. Because looping over 200 lights per pixel over 4 depth peels is not going to be happening, right? That's not going to cut it. So what we want to do there is think about ways we might get more lights into our system. And there's a lot of ways you can do that, but we got to kind of think about how we would want to handle situations where we would have lots of lights, right? So the second thing we really want is we want to have light that isn't just direct. Because all we're simulating right now is a particular light source shines directly on an object and we see it. Now, as you can see from the results of that, it looks pretty convincing for something like, you know, a flashlight. Because something that's a very bright light source in a very dark area that doesn't have, well, I shouldn't say that. What I really mean to say is a very dim light source in a very dark area doesn't bounce a lot of secondary light around, so it kind of looks reasonable when you look at something like a flashlight effect. This is more reasonable. So you can see what our lighting looks like is exactly what our lighting is. Zero bounce lighting, so it's kind of the equivalent of shining a flashlight, which is a very dim light, right, compared to the sun or something, very dim, in a dark room. And so you just see these very harsh lighting effects, and that's good for that particular situation. But if you want a softer look, more like a sunlight where there's a lot of bounce light around, so even things that are in complete shadow still have a lot of illumination to them from the surroundings, things bounce with the surroundings, we're not getting that. Right? So that would what we want out of number 2 is some way to get some ambient lighting in there, right? Some lighting that's just about light that bounces around the environment and lights things up instead of having to come directly from a light source that we're computing. And number 3 would be surface variability. Okay? So surface variability is just a way of saying we would like some way to know what a particular surface's reflectance properties actually are, and then we'd like to treat the light that bounces off that surface differently, right? Now, we haven't talked very much about reflectance functions, but we mentioned a little bit of it, right? A very diffuse reflector is one that takes light from any angle and scatters it to any angle. It's like a chalky wall paint or something, where there isn't a lot of reflection in it directly. You don't see whole shapes or images reflected in it, not much gloss. You just see light that is the general amount of light that's hitting it is what you see. Very diffuse, very chalky. All the way to the other end of the spectrum is like a mirror, something that literally scatters light only out the direction it comes in. So like it comes in and it goes out the exact opposite bounce, like a ball bouncing off the surface, right? And it doesn't scatter hardly at all. So when you look at a mirror, you don't see any indication of how much light in general is falling on that part of the surface. Instead, you only see the light that was coming from a very specific direction. And that's what makes it a mirror, right? And so, you know, getting some surface variability in there is what allows you to communicate to the player that surfaces are different types of material. So for example, if you want something to look wet or like water, that's a very highly reflective surface. You want something to look chalky like a wall or a piece of stone that's not very reflective. That is more towards the diffuse side. And so being able to vary surfaces a little bit can add a lot of visual interest to the game. I don't know that we want that too much in Handmade Hero or need it too much in Handmade Hero, but it's just worth noting. And so we'll talk about trying to upgrade to do some of those things next week, but for the time being, we could actually augment what we're doing right now to take a little bit of that into account. Let's take a look, for example, in our shader, right? Let's say that in our shader, we wanted to start taking into account the viewing direction, right? So where the viewer was. Well, we should know where the viewer was, generally speaking, because our transform tells us where the viewer is, right? Our transform, I believe, I think should tell us where the viewer is. I mean, it might be something we would kind of have to reconstruct, so it might be better to just pass it down because, well, here, you can see. I mean, we already know what the answer is here, so I'll just show it to you. But so when we do set camera transform, right, here is like our equation for the camera. So we say, oh, here's the Z rotation, X rotation. We take, you know, how we're viewing the world. We take the camera translation, and we produce, like, this is, I guess, the debug right version of that. And in order to produce the camera's final position, we just say rotate it by whatever that rotation is and place it out there, right? But then I think, if I'm not very much mistaken, when we do set camera transform and you take in that camera position, I think, don't we do, yeah. So when we actually specify the projection matrix, right, we have to multiply the camera position. Where Where is that happening? We have to multiply the camera position by the rotation itself, right? To sort of produce what will be the correct effect after things are rotated. And so if we wanted to recover that out, we would have to invert the transform to get it back. So what we really need in this case is for our camera to still preserve that piece of information. So when we do render setup and we pass down that camera P, I think what we'd want to do is just provide that to the vertex shader, or the, well, any shader really, that wants it. We would want to still set that up, right? Oh, and it looks like we do, right? So there's that camera P. So we're getting that camera P directly, and that is really all we will need. So in here, we don't use it in the fragment shader yet. We only use it, I guess, in the vertex shader right here. But if we want to use it, we can also access it, since it's already being specified, we can access it in here as well. So we can just get the camera P and the light P. That means producing this vector that we want, which is to camera, is just as simple as what we were doing before, right? There's the camera distance, which is what we want there, and we can normalize that one as well. And then we can have the cos cam angle is dot to camera world n. And now we know the angle to the camera as well as the angle to the angle to the light source. Now, what we may want to do here is then create a sort of we can do a bunch of different things here, right? One of the things we can do here is we can now start to make our reflectance be based on the angle. So if we wanted to create a mirror surface, what we'd basically be saying is we want the angle to the camera and the angle to the light source to be at 90 degrees to each other, right? So what I could actually do here is say something like, okay, this is like the cosine of the camera and the light, right? So I could say, take the camera, take the light, do the dot product there. Let's clamp that. And now we could say, well, in addition to modulating this with the incident of the light, we could say that, well, now what we're going to do actually is pretend this is a mirror. We could use this entirely instead, right? So we could say whatever the angle is between these two, that's what it's going to be. Now, you know what? Let me do this a slightly different way, because that's not going to give us quite this. This is going to make it a little bit too hard for us to do it. So let me do it slightly differently. Let's say I just want to do the reflection, right? So what I want to do is I want to say, well, we've got our diffuse light, and that's here. So let's name these diffuse light. So this is the light strength. This is the diffuse amount, right, times this cosine angle. So you could think of this as saying diffuse coefficient, right? So let's say the diffuse coefficient right now is 1.0. And so that's going to give us the lighting that we already have. Then what we want to do is we want to produce another thing here, which is going to be our specular coefficient, right? It's going to be that light that comes out in a mirror style. Again, this is a really basic way to do lighting, but let's say we have a specular light amount here. So we do specular C times, you know, whatever this thing is, something, times the light strength. And what I probably want to do is like make a term here for this. And these may be different things, right? We may want different colors for these, for example, in the future and so on as well. But for right now, we want something there, and we want that to multiply the light strength as well. And then what we'll do is we'll sum up our light. So the amount of light we get here plus the amount of light we get here. And really, if you think about it, these should always have to sum to 1 if this is a realistic surface. So we could say that this is a half diffuse, half specular surface, right? Because we can't reflect out more light than we took in. So whatever the light strength is coming in, we should expect to have that same amount at maximum bounce back, right? And we can come up with, basically coming up with real reflectance functions is about tuning these things to be more realistic curves and so on. But we'll, again, move on from that. We're just going to do a basic little reflection here. So what I need to do here is like a cosine reflected angle function. And so what I want to do is say, okay, we've got the camera, we've got our diffuse light amount. So then what I want to do is I want to take another thing here, which is going to be like the cos reflected angle, which is going to be the dot product of the light with the reflection, which is the reflection vector. And we'll talk about what that is in a second. So what I need here is some kind of reflection vector. This is going to give me that thing that I want, and I'm going to clamp it again just like I did. That will give me the amount of specular light contribution. Okay. So what's a reflection vector? Well, a reflection vector, what I want to do, what I'm trying to set up here is I've got my to light vector, right? It goes out this way. I've got my viewing direction, right? And what I want to do, and I guess what I should say is, the viewing direction looks like that, right? What I want to do is come up with, if this was coming in at this angle, and maybe, that I can emphasize the difference between the two, maybe let's say, instead, let's say this is the way I'm viewing it. What I want to do is reflect that vector out, like so. So I would get where am I looking if this were a perfect mirror? What should it reflect if it was a perfect mirror? And then I can dot these two together to see how close I am to my mirror reflection. Then that will give me how much of that mirror contribution I should get, right? The specular light amount. Okay. So if I wanted to do that, how do I produce the reflection vector? Well, I know I've got this vector, which is the vector to the camera. So let's say I negated that vector to the camera. I would get the vector I wanted, essentially, but it would be pointing down the it would be pointing, essentially the wrong direction. It's pointing downward, and I want it to be pointing upward, right? So how do I reflect that about this line? Well, it just so happens that because I have the surface normal, I'm in a really good position to compute exactly how to do that. Because the dot product of the normal with that vector, right? So n dot c is going to give me exactly the amount that I wanted. Now, if this looks familiar to you, it should. We did this for physics, for bouncing, right? We computed this reflection for bouncing our particles. And I don't remember if we also, I think we may have done it for bouncing when we were moving objects around. So I know that my n transpose c here will give me how far along the normal I am, right? And that's going to be a negative value because I'm under, I'm basically under the normal, if you will. So if I want to then move myself back up to where I would be, what I can do is just subtract 2 of that, right, to move myself up to pointing back as the reflected amount. The first n transpose c moves me to the horizon, to the equivalent line, so that gets rid of any vertical displacement. And the next one gives me back that same vertical displacement in the opposite direction, right? Now, remember, n transpose c is only if this were the c vector, but I actually computed the c vector going this way. So it's really n transpose negative c, which is negative n transpose c, which means this negative cancels out, which means it's actually 2 ntc, right? If that makes sense. Which is a little bit weird, to say the least. But anyway, so let's work that out exactly, so we can actually do it. Okay. So here's our camera. That's 2 camera. And it's supposedly unit length, right? Here is our normal vector. And what we want to do here is pretend we have negative c, There's our negative c. We want to know where on the n vector we are, right? So in order to do that, we do n transpose negative c. And the negative should distribute there because it's a linear operator. So that should be negative n transpose c, right? So that's negative n transpose c. Oops. Is negative n transpose c. Is that distance right there, right? So now if we take negative c, and we now want to bring negative c up to here, right? And then up to where it should be in order to produce the reflected vector. I need to add this twice, right? So I need to add to it, well, I need to add this to it twice, and this is going in the wrong direction, right? So I really need to subtract it, if that makes sense, in order to get it going in the right direction. So I need to subtract 2 times negative n transpose c, like so, in order to get my new reflected vector, right? So I start with negative c, I subtract 2 times that, and I need a direction, because remember this is vector math, so I can't take a vector and this is a scalar, right? So what direction am I going along? Well, I'm going along n, right? So this is this far along n. So again, start at negative c, figure out how far along n I am under the surface, and then I just subtract twice that along n to put me back over the surface. And there's my reflection vector. Now there's a lot of negatives in there, so really I could just say this is negative c, this negative comes out, so it's really just plus 2 n transpose c n. And that's all there is to it, I think. So in theory, we should be able to compute this, the reflection vector here. So we've got negative c, and that is our 2 camera function. We have plus 2 times the dot product of the world normal and the camera, like so. And that's times the normal. That should give us the reflection vector. That reflection vector gives us what we want to dot product with in order to determine how much we're looking directly at the light. Yeah, in theory, that's the correct lighting computation for a more specular surface. Now, it's hard to tell whether we did that correctly, obviously. But what we should see now, and of course I am seeing it, is we should be able to see, I don't know if you can see this, but as I sort of look down, I get the light source. There's a highlight on the light source, right, which kind of comes at me, right? You can see that, right? That didn't used to. And what we can see that's a little bit weird here, right, is this is still a very glossy, diffuse reflection. The reason for that is that the reflected angle that we compute, remember, we're going to be adding some of that specular contribution based on a very wide angle, because when we're right on, the cosine will be 1. But even as we spread out and start to look at wider angles, the cosine fall off is not particularly sharp, right? It still falls off cosine angle, so we're going to collect a lot there. So if we want a tighter, more mirror-like surface, we can choose to start making that curve be more than cosine fall off. So for example, once we produce cosine reflected angle, we could choose to square that. And we could choose to square that a couple times if we wanted to really crank down the sort of the tension of that highlight. And what you can see if we do that is once we make that happen, you can see our specular highlight gets much tighter, right? And what you can see too is that, this again gets into the non-physical aspect of our lighting. This was a conservative way of making sure the two things don't sum together, but what we could do, what we end up doing there is killing a lot more light than we should. So what we really want to do there is actually figure out how to make that a more fair distribution. At the moment, what we could say is, let's make the specular very bright and very tight. Just totally fake, right? Not correct lighting. But it just accentuates it so you can see it, right? So here's a pretty, here's a pretty high specular power, right? And now you can see that we've got that shine on the light there. And so you can see as it goes, right, we're getting that sort of, as I'm moving the hero around, you see that very clear specular highlight moving with him. And as the viewing angle changes, so does that specular highlight. Again, power-wise, you can crank it as high as you want. Yeah, I'm just squaring, right? So there's a very tight specular highlight you can see. Again, we're not computing any shadows, so you still get a specular highlight down there, right? And so on. And that's just, again, just a really simple, very, very simple. This is basically like kind of crappy Phong shading now, right? If you've ever heard of that. Which is basically just saying we have one specular term, we have one diffuse term. The specular term is raised to some power and, you know, tweak as you wish, right? But you can already see how that kind of gives you more of a sense that this surface has some shadowiness to it. And if we were to kill the diffuse light more, so let's say we were to take this diffuse light down to a very low level, you can start to see how it starts to sort of look more mirror-like. Now again, the only thing we're reflecting is the light though. So that's why it doesn't look like a real mirror, because we're not reflecting all of this other light that's bouncing off surfaces. Again, that's the thing with direct light. We're only reflecting literally the light. So now we've got a pretty mirror-like surface here in terms of how the light behaves. And again, the further you crank that power, the more you will see that happen, right? So if I just continue to crank that power more and more, that highlight would tighten and tighten and tighten into what's more like a direct reflection of the light source you can see there, right? All right, so I think that's a good place to end for today, now that we've got the basics of like a Phong, you know, kind of crappy Phong lighting in there. That's it. That's all I'm going to do for today. So next week we'll look a little bit more. The problem you could not find when you thought about dividing by cosine phi is that the only reason diffuse surfaces can exist, this is Desu, just was trying to answer one of the questions I posed on the stream, can exist is surface roughness, which invalidates the assumption that you will collect photons from the entire surface. Roughness blocks some photons. One trick is to check your model. A photon must have the same probability of going one way as the opposite way. All formulas for diffuse light are approximations, and all diffuse surfaces are different. In order to render a physically correct diffuse surface, you'd have to measure a four-dimensional data set of light distribution reflectance depending on two angles of incidence. Yeah, which would be like the whole BRDF for that surface or something. I'm not sure that still just answers my question in terms of like, I mean, I still would like to see it written out a little more clearly as to how the light is bouncing around. Just to see a diagram, you know? You're a sniper. GLSL has a reflect function. Yeah, I don't tend to use the GLSL reflect function though. I always write the reflect function myself. And the reason for that is just because I may want to modify things in it. I find that that's a little bit too much. Kind of like how, you know, sometimes I use the normalize function there, but most of the time I write the normalize myself as well because I need to do something in between. MTS Mox, should you normalize the world end in the fragment shader? I don't believe so. As I discussed on the stream earlier, because all our surfaces are flat, there shouldn't be any situation where our world normals are not normal because they're not actually being interpolated, if that makes sense. BA6IX says, ever done website dev work? Well, I did the our website, Molly Rocket. If that's what you mean. Uplink coder, can you take a quick shot at reducing the banding? No, we can't really do that quickly. That is something that is just about introducing dithering, because there is no actual banding in color space. They're actually colors that are exactly next to each other. So the fact that you can see banding is just because the monitored resolution is only 8-bit color, right? So to get rid of the banding, what we have to do there is we have to introduce a dither step, which is not going to be quick, I don't think. We have to just, at the end, when it goes to convert 16-bit color, which we are now storing, to 8-bit color, it'll dither. Uplink coder. Also, I opened an issue where the game crashes when you go backwards after starting the game. Go backwards. Did you put that in here in a... Are you just talking about this one? Yeah, that, I mean, we can... That's like in the game entity code, which we have not really done anything with. So there's, that stuff is all totally placeholder, right? That reminds me, this needs to get finished. I should just do this one. This was someone wanted a change for, they were compiling in Visual Studio 2017. And I tried to fix it for them, but I messed up the thing they were asking for. They were asking for getting rid of make-int resource. I think in both places. So I believe that's what they wanted. So we've removed make-int resource in both. So that was just something they wanted for compiling on Visual Studio 2017. Let's see. TTBJM, would HDR tone mapping be worth implementing? Yeah, it's usually worth implementing. I don't know that we might be getting a little far from the scope of Handmade Hero if we start doing HDR rendering, though. So I don't know that I really want to go down that route. But usually, yeah, it is worth it. So So as that's the kid, is bump mapping a feature you're looking into implementing? So bump mapping is really an art problem, not an engine problem. It's trivial to implement in the engine. So in here, where you get the world normal, all you really have to do is, instead of just using the world normal, you load the normal out of a texture. That's it. So there ain't a lot to it. So really the problem is that the sprites have to have normal maps. And in order to have them have normal maps, you have to have some art process that's going to produce those. Like either they have to be painted with like bump, you know, like sort of diffuse maps by your artist, or they have to be post-processed with a tool like Sprite Lamp or something. And I don't really know if I want to go down that road either. But there isn't a lot to it. Like, you don't have to do a lot of work to add it. There is a modicum of work because you depending on how you want to do it, you may want to send down more than just the world space normal. So right now we're sending down world n. But if you think about it, world n is not enough to specify the facing direction of a surface because it doesn't specify the tilt. So depending on what kind of lighting effects you want to do, you may want to send down a full three-dimensional axis system or a quaternion that you then convert to one if you want to save vertex bandwidth. So there's like a slightly more work has to be done to pass down a full reference frame instead of just a world normal. And the other thing you have to do is every texture now has to have a bump map, right? Or a normal map. Preferably a normal map. They are higher quality than a bump map. Jezzy23 says, SIMD on CPUs are pretty cool, however it sounds painful to make use of the newest and the best instructions while remaining compatible with old CPUs. I don't see programs being compiled separately for different SSC capabilities. I assume a program will just crash. If the CPU encounters an unsupported instruction, would you dispatch at runtime for different code paths to flexibly use supported SIMD instructions? Does it sound like dumb? Yeah, so that's not really the problem. The problem is actually somewhat amusing. If you want to optimize your game for newer instruction sets, like AVX 512 or AVX2, whatever, rather than SSC2 or something that's universal supported, SSC2, SSC3, this isn't that hard to do. You just pick the few functions that you probably, because you got to hand optimize that anyway, right? Because you've got to go make use of intrinsics usually if you're going to get any good performance out of SIMD most of the time, or use an automatic thing like Intel IPC or something. So you've done some work to isolate what it is you're actually going to compile via that path. And once you do that, it's not that hard to just have one or two versions of that function that you just set the pointer to at startup by checking the CPU capabilities and then setting the function pointer, right? So it's not very hard. It's kind of exactly like we do with OpenGL, where we check extensions and then set the extension. That's about all you've got to do, right? So that part's not particularly hard. Here's the real problem, and why we're not doing it on Handmade Hero, and why probably no one really ever does it unless they get paid by Intel or AMD to do it. And that is because you're optimizing the case you don't need to optimize, right? Because if you think about what happens is, your worst performing CPU is going to be the one that doesn't have that instruction set. So if the game runs on SSE2 on an older CPU at all, then it's going to run great on an AVX512 supporting CPU. It's going to run gangbusters on that. So you have no need to optimize it with AVX512 because it's already way faster than your minimum spec computer that doesn't have AVX512. So paradoxically, you end up never really caring about something like AVX512 until it's actually available on lots of CPUs on your minimum spec, because then you can use it on the minimum spec to make that minimum spec perform as well as your high spec machine, which doesn't really need you to do it, right? But when AVX512 or something is only available on your high spec machine, forget it. You can't. It's worthless. You can't use it for anything. The only way you can possibly use it is if you have some isolated effect that can be turned off on the lower end CPU, right? So typically what actually happens in practice is that you don't ever need to do two versions of the code, one for the AVX512 and one for SSE2. Typically, you only do the AVX512 version, you check the CPU bits, and if it doesn't support AVX512, you turn that feature off. So you're never even going to call, you're not going to call an SSE2 version of it, it's over, right? That feature's not there, whatever that feature was. Realistic deformation physics of blobby whatever is off, it's gone, forget it's not there, right? And so basically, you know, you really don't have the use case that at least that I can think of I'm trying to run the exact same thing on something that has AVX512 and something that doesn't, and I need to optimize the AVX512 part. I can't even think of a way that would happen. You always have to have some additional thing you're turning on. And I mean, maybe if it's just something that's so pure quantity, like how many particles am I doing with this thing? Then maybe that's why you optimize 512, because then the higher machine can have 10 times as many particles or something. But you know, you can see why I'm sort of saying it's rare that you're running literally exactly the same thing in both cases and have to optimize the AVX512 one. Because typically that chip just doesn't need any optimization. It can run exactly the same thing, the SSE2 version, and it's way faster already because it's a more modern CPU with more optimizations and possibly higher clock sometimes, who knows, more cores certainly. And Jizzy, yes, what you just said about what if you have a deal with Intel to benchmark higher on the newest hardware, like I said, that's the case that, remember when I said if you have a deal with Intel or AMD or something like that? That's exactly what I mean. And that's fine, right? That's a totally worthwhile thing because optimizing for new instruction sets is usually pretty fun. Programmers oftentimes enjoy doing it. So if you can get a hardware company to subsidize the cost for you, then that just lets you add a high-end feature to your game that will only work on AVX512, let's say, and everybody wins. You got to do some fancy feature that you couldn't have justified otherwise because you know you're not going to sell more copies of the game to the 10,000 people who have AVX512. Like, they're not going to not buy the game just because it didn't have an AVX512 feature. But now, if Intel's willing to subsidize that development cost, you know, if they're willing to pay you 50 grand or something, then, you know, that's worth it. Because now you can add a feature to your game. They paid for it. Your players get the benefit of it if they happen to have AVX512. And you got to do a fun programming thing. So, you know, everyone wins in that scenario. But that doesn't happen very often. You know, not that many people have deals with Intel to optimize stuff on their latest hardware or add features that can only be exposed by having, you know, more cores, more instructions, whatever. But if you do, then that's the scenario where you'd see that, right? Jim00 says, any plans to create different types of lighting, as in room X is lit like a summer's day while room Y is contrasted and dark like a film noir, or would you have all this done in the art assets maybe? Yeah, no, I do think we will change the lighting, the lights per area, for sure. Some areas will like be lit mostly by, you know, point lights like we've got now, and others will have like a sun or a moon lighting kind of a thing, I think. So I do suspect we'll do a little bit of that. I don't think we'll get too crazy, but we're going to do a little bit of that over the next couple of weeks. All right. Let's go ahead and close things down here. Go. All right. Thank you, everybody, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along the series at home, you can always pre-order the game on handmadehero.org, and it comes with the source code so you can play around with it. We also have a forum site you can go to if you want to ask questions, a Patreon page you can go to if you want to support the video series, a schedule about the sets we're going to be live, and an episode guide that lets you know what happened in the past so you can find out what we already covered. That's about it for this week. I'll be back next week when we'll do a little bit more work with the lighting. Try to put a little bit more advanced stuff in there than what we've got right now. Until then, thank you for joining me. Have fun programming, and I'll see you on the internet. Take it easy, everybody.